Welcome. In this video, we will explore the fundamentals of linear algebra, a branch of mathematics essential for understanding many modern technologies. Our focus will be on systems of linear equations and a powerful method for solving them called Gaussian elimination. By the end of this session, you will be able to: first, define and identify linear equations and systems of linear equations. Second, represent these systems using augmented matrices. Third, apply elementary row operations to solve systems of 2 and 3 variables. And finally, analyze the number of solutions a system can have: a unique solution, no solution, or infinitely many solutions. These skills are crucial for the IB Mathematics, Analysis and Approaches higher level curriculum. Let's begin with the fundamental building block, the linear equation. A linear equation in n variables, x1 through xn, is an equation that can be written in the form a1x1 plus a2x2 and so on up to a(n)xn equals b. Here, v, a values, and b are constants, and the key characteristic is that the variables are only raised to the power of 1. There are no products of variables, no square roots of variables, and no variables in the denominator. For example, 2x equals 3, 4y equals 7, and 3x minus y equals 4 are all linear equations. Notice how the variables x and y are only to the first power. Now, let's look at some examples that are not linear equations to clarify the definition. First, 2x plus y plus xy equals 3. This is not linear because of the xy term, which is a product of 2 variables. Second, x1 minus x2 minus 2x3 squared equals 0. This is not linear because the x3 term is squared. Third, x equals 7 minus the square root of y. This is not linear because of the square root of y term. So, to recap, a linear equation has variables only to the first power, with no products or roots of variables. A solution to a linear equation is a set of values for the variables that makes the equation true. Let's consider the equation x1 plus 2x2 minus 3x3 equals 8. Is the set of values x1 equals 3, x2 equals 4, and x3 equals 1 a solution? Let's substitute these values into the equation. We get 3 plus 2 times 4 minus 3 times 1, which simplifies to 3 plus 8 minus 3, which equals 8. Since 8 equals 8, this set of values is a solution. Now let's test another set. x1 equals 11 over 3, x2 equals 13 over 3, and x3 equals 2. Substituting these values, we get 11 over 3 plus 2 times 13 over 3 minus 3 times 2. This is 11 over 3 plus 26 over 3 minus 18 over 3, which equals 19 over 3. Since 19 over 3 does not equal 8, this set of values is not a solution. A single linear equation with more than one variable will have infinitely many solutions. We can describe this set of solutions using parameters. For our equation, we can let x2 equal a parameter s, and x3 equal a parameter mod t. Substituting these into the equation and solving for x1 gives us x1 equals 8 minus 2's plus 3t. This parametric form describes all possible solutions. A system of linear equations consists of 2 or more linear equations that we want to solve simultaneously. A solution to a system is a set of values for the variables that satisfies every equation in the system at the same time. Let's consider this system of 2 equations with 3 variables. Let's test the solution we found earlier for the first equation. x1 equals 3, x2 equals -1, x3 equals 1. We know it satisfies equation 1. Let's check equation 2. Substituting the values, we get 3 plus -1 minus 3 times 1, which is 3 minus 1 minus 3, equaling -1. Since -1 does not equal 2, this set of values is not a solution to the system. Now let's test another set. x1 equals 11 over 3, x2 equals 13 over 3, x3 equals 2. We already know this set does not satisfy equation 1. Therefore, it cannot be a solution to the system. My apologies, I made a mistake in the previous scene. Let's reevaluate the second solution for the system. Let's recheck the solution. x1 equals 11 over 3, x2 equals 13 over 3, x3 equals 2. For equation 1, we have 2 times 11 over 3 minus 13 over 3 plus 4 times 2, which is 22 over 3 minus 13 over 3 plus 24 over 3, totaling 33 over 3, which is 11. This is correct. For equation 2, we have 11 over 3 plus 13 over 3 minus 3 times 2, which is 24 over 3 minus 6, or 8 minus 6, which is 2. This is also correct. Since this set of values satisfies both equations, it is a solution to the system. This highlights the importance of checking all equations. Systems of linear equations can be classified based on their number of solutions. A system is called consistent if it has at least one solution. This means it could have a unique solution or infinitely many solutions. Conversely, a system is called inconsistent if it has no solutions at all. Consider the system x plus 2y equals 3 and x plus 2y equals 4. If we subtract the first equation from the second, we get 0 equals 1, which is a contradiction. There are no values of x and y that can satisfy both equations simultaneously, so this system is inconsistent. We can also classify systems by comparing the number of equations, m, to the number of unknowns, n. A system is underspecified if it has more unknowns than equations. For example, 2 equations with 3 variables. If an underspecified system is consistent, it will always have infinitely many solutions. A system is overspecified if it has more equations than unknowns. For example, 3 equations with 2 variables. Overspecified systems are often inconsistent, but they can have a unique solution or infinitely many solutions in special cases. To solve systems of linear equations systematically, we use a powerful tool called an augmented matrix. An augmented matrix is a rectangular array of numbers that represents a system of linear equations. We simply write down the coefficients of the variables in the constants, leaving out the plus and equal signs. For a general system of m equations and n unknowns, the augmented matrix will have m rows and n plus 1 columns. The vertical line separates the coefficients from the constants. Let's look at an example. Consider this system of 3 equations with 3 variables. The first equation is 2x minus y plus z equals negative 1. The coefficients are 2, negative 1, and 1, and the constant is negative 1. This forms our first row. So the first row of the matrix is 2, negative 1, 1, and negative 1. The second equation is x minus 3, z equals 4. Notice there is no y term. This means its coefficient is 0. So the coefficients are 1, 0, and negative 3, and the constant is 4. This is our second row. The second row is 1, 0, negative 3, and 4. The third equation is negative x plus 2y minus z equals 0. The coefficients are negative 1, 2, and negative 1, and the constant is 0. This is our third row. The third row is negative 1, 2, negative 1, and 0. Putting it all together, this is the augmented matrix for the system. Each row represents an equation, and each column represents a variable or the constant term. Now that we can represent systems as matrices, how do we solve them? The key is to use row operations. Row operations are a set of rules that allow us to manipulate the rows of an augmented matrix without changing the solution set of the corresponding system of equations. There are 3 types of elementary row operations. First, we can interchange any 2 rows. This is equivalent to swapping 2 equations in the system. Second, we can replace a row by a non-zero multiple of itself. This is equivalent to multiplying an entire equation by a constant. Third, and most importantly, we can replace a row by the sum of itself and a multiple of another row. This is the matrix equivalent of the elimination method you may have used for 2x2 systems. Let's see these in action with an example. Consider the system 2x plus y equals negative 1 and x minus 3 y equals 17. Its augmented matrix is 2, 1, negative 1 in the first row, and 1, negative 3, 17 in the second row. If we interchange row 1 and row 2, we write R1, double arrow, R2. The resulting matrix has the rows swapped. This system has the exact same solution as the original. If we multiply row 1 by negative 3, we write negative 3, R1, arrow R1. Every element in the first row is multiplied by -3. The solution set is unchanged. Finally, let's replace row 2 with twice row 2 minus row 1. We write 2r2 minus r1 arrow r2. We calculate 2 times the second row, then subtract the first row, and the result becomes the new second row. This operation is the most powerful for eliminating variables. Our goal in solving a system is to use row operations to transform the augmented matrix into a simpler form from which we can easily find the solution. This process is called row reduction. For a 2x2 system, we aim to get a 1 in the top left corner and a 0 in the bottom left corner. This eliminates the first variable from the second equation. Let's solve a 2x2 system using this method. Consider the system 2x plus 3y equals 4 and 5x plus 4y equals 17. The augmented matrix is 2, 3, 4 in the first row, and 5, 4, 17 in the second. First, let's get a 0 in the bottom left corner. We can replace row 2 with 2 times row 2 minus 5 times row 1. This will eliminate the x term from the second equation. So, we perform the operation 2r2 minus 5r1 arrow r2. The first row remains unchanged. For the second row, we calculate 2 times 5 minus 5 times 2, which is 0. Then 2 times 4 minus 5 times 3, which is -7. And 2 times 17 minus 5 times 4, which is 14. Our new matrix is 2, 3, 4 in the first row, and 0, -7, 14 in the second. Now let's simplify the rows. We can divide the first row by 2 and the second row by -7. We perform the operations 1/2 r1 arrow r1 and -1/7 r2 arrow r2. The first row becomes 1, 3 over 2, 2. The second row becomes 0, 1, -2. This is our simplified matrix. This matrix corresponds to a new system of equations. The second row tells us that 0x plus 1y equals -2, which means y equals -2. The first row tells us that 1x plus 3 over 2y equals 2. We can now substitute y equals -2 into the first equation. This gives us x plus 3 over 2 times -2 equals 2, which simplifies to x minus 3 equals 2. Solving for x, we find x equals 5. The unique solution to the system is x equals 5 and y equals -2. Let's now extend this method to solve a 3x3 system of linear equations. For a 3x3 system, our goal is to reduce the augmented matrix to row echelon form. This means we want a 1 in the top left corner and zeros below it in the first column. Then, we want a 1 in the second row, second column, and a 0 below it. Finally, we want a 1 in the third row, third column. This creates a triangle of zeros in the bottom left. Let's solve the system x plus 3, y minus z equals 15, 2x plus y plus z equals 7, and x minus y minus 2z equals 0. First, we write the augmented matrix. The first row is 1, 3, -1, 15. The second is 2, 1, 1, 7. The third is 1, -1, -2, 0. Our first step is to create zeros in the first column below the leading one. We'll use row 1 to eliminate the 2 in row 2 and the 1 in row 3. We perform the operations r2 minus 2, r1 arrow r2, and r3 minus r1 arrow r3. The first row stays the same. The new second row is 0, -5, 3, -23. The new third row is 0, -4, -1, -15. Next, we need to create a 0 in the second column of the third row. We'll use row 2 to eliminate the -4 in row 3. We perform the operation 5r3 minus 4r2 arrow r3. The first two rows stay the same. The new third row is 0, 0, -17, 17. Finally, let's simplify the rows to get the leading ones. We perform the operations -1/5 r2 arrow r2 and -1/17 r3 arrow r3. The matrix is now in row echelon form. Now we can use back substitution to find the solution. The third row gives us z equals -1. Substituting this into the second row's equation, y minus 3/5 times -1 equals 23/5, which gives y equals 4. Substituting both z and y into the first row's equation, x plus 3 times 4 minus -1 equals 15, which gives x equals 2. The unique solution is x equals 2, y equals 4, and z equals -1. Not all systems have a unique solution. Let's see what happens when a system is inconsistent, meaning it has no solution. Consider the system x plus 2y plus z equals 3, 2x minus y plus z equals 8, and 3x minus 4y plus z equals 18. The augmented matrix is 1, 2, 1, 3 in the first row, 2, -1, 1, 8 in the second, and 3, -4, 1, 18 in the third. First, we eliminate the x terms in the second and third rows. We perform R2, minus 2, R1 arrow R2, and R3, minus 3, R1 arrow R3. This gives us a new matrix with zeros in the first column below the leading one. Now, let's eliminate the y term in the third row. We perform the operation R3 minus 2R2 arrow R3. The first two rows remain the same. The new third row is 0, 0, 0, 5. Let's interpret this final row. The third row corresponds to the equation 0x plus 0y plus 0z equals 5. This simplifies to 0 equals 5, which is a false statement. This contradiction means there are no values of x, y, and z that can satisfy the original system of equations. Therefore, the system is inconsistent and has no solution. The third possibility is that a system has infinitely many solutions. This occurs when the equations are not independent. Consider the system 2, x minus y plus z equals 5, x plus y minus z equals 2, and 3x minus 3y plus 3z equals 8. The augmented matrix is 2, -1, 1, 5 in the first row, 1, 1, -1, 2 in the second, and 3, -3, 3, 8 in the third. Let's start by eliminating the x terms in the second and third rows. We perform the operations 2r2 minus r1 arrow r2 and 2r3 minus 3 r1 arrow r3. This gives us a new matrix with zeros in the first column below the leading two. Now, let's eliminate the y term in the third row. We perform the operation r3 plus r2 arrow r3. The first two rows remain the same. The new third row is 0, 0, 0, 0. Let's interpret this result. The third row corresponds to the equation 0 equals 0. This is a true statement, but it provides no information about the variables. It indicates that the third equation was a linear combination of the first two, meaning it was redundant. We are left with two independent equations and three unknowns, which will lead to infinitely many solutions. To find these solutions, we introduce a parameter. Let's set z equal to a parameter, t. The second row gives us 3y minus 3z equals -1. Substituting z equals t, we get 3y minus 3, t equals -1, so y equals t minus 1/3. Now substitute y and z into the first row's equation. 2x minus t minus 1/3 plus t equals 5. This simplifies to 2x plus 1 divided by 3 equals 5, so x equals 7/3. The solution set is x equals 7/3, y equals t minus 1/3, and z equals t, where t can be any real number. This describes an infinite line of solutions in 3D space. Let's work through a more complex example, which is typical of IBHL questions. We'll consider a system with a parameter. Consider the system x minus 2y minus z equals -1, 2x plus y plus 3z equals 13, and x plus 8y plus 9z equals a, where a is a real number. The augmented matrix is 1, -2, -1, -1 in the first row, 2, 1, 3, 13 in the second, and 1, 8, 9, a in the third. First, we eliminate the x terms in the second and third rows. We perform R2 minus 2 R1 arrow R2 and R3 minus R1 arrow R3. This gives us a new matrix. Now, let's simplify the second row by dividing by 5. We perform the operation 1/5 R2 arrow R2. The second row becomes 0, 1, 1, 3. Next, we eliminate the y term in the third row. We perform the operation R3 minus 10 R2 arrow R3. The new third row is 0, 0, 0, a minus 29. Now we can analyze the number of solutions based on the value of comma a. The third row corresponds to the equation 0 equals a minus 29. If a is not equal to 29, then the equation becomes 0 equals a non-zero number, which is false. In this case, the system is inconsistent and has no solutions. If a is equal to 29, the equation becomes 0 equals 0, which is true. This means the third equation is redundant, and we have infinitely many solutions. Let's find the solutions for the case where a equals 29. We let z equal a parameter, t. From the second row, y plus z equals 3, so y equals 3 minus t. From the first row, x minus 2, y minus z equals negative 1. Substituting y and z, we get x equals 5 minus t. The solution set is x equals 5 minus t, y equals 3 minus t, and z equals t. Let's apply these techniques to a common IB problem type, finding the equation of a quadratic function that passes through 3 given points. The general form of a quadratic function is y equals ax squared plus b, x plus circa. Our goal is to find the values of the coefficients a, b, and c. Since the function passes through these points, each point must satisfy the equation. This will give us a system of 3 linear equations in the variables a, b, and c. For the point 1 minus 2, we substitute x equals 1 and y equals negative 2 into the equation, giving us a plus b plus c equals negative 2. For the point 2, 4, we substitute x equals 2 and y equals 4, giving us 4, a plus 2, b plus c equals 4. For the point 3, 12, we substitute x equals 3 and y equals 12, giving us 9a plus 3, b plus c equals 12. We now have a 3 by 3 system of linear equations. Let's write its augmented matrix. Now we perform row operations to solve for a, b, and c. First, we eliminate the char a terms in the second and third rows. We perform R2 minus 4 R1 arrow R2 and R3 minus 9 R1 arrow R3. Next, we eliminate the b term in the third row. We perform R3 minus 3 R2 arrow R3. The matrix is now in row echelon form. We can use back substitution. The third row gives us c equals negative 6. The second row gives us negative 2, b minus 3, c equals 12. Substituting c equals negative 6, we find b equals 3. The first row gives us a plus b plus c equals negative 2. Substituting b and c, we find a equals 1. Therefore, the equation of the quadratic function that passes through the 3 given points is y equals x squared plus 3x minus 6. Let's conclude with a quick summary of what we've covered. We started by defining linear equations and systems of linear equations. We learned how to represent these systems using augmented matrices, which are a compact and organized way to handle the coefficients and constants. We then introduced the 3 elementary row operations, interchanging rows, multiplying a row by a non-zero constant, and adding a multiple of one row to another. These operations are the foundation of Gaussian elimination. Finally, we saw how to use these operations to solve systems of 2 by 2 and 3 by 3 equations. We analyzed the 3 possible outcomes: a unique solution, no solution, and infinitely many solutions, and learned how to identify each case from the row-reduced matrix. Mastering these concepts is crucial for success in IB mathematics, AAHL. Now let's move on to some practice questions to solidify your understanding. Here are 5 practice questions designed to test your understanding of the concepts we've discussed. I encourage you to pause the video and attempt them on your own before watching the solutions. Question 1. Solve the system of equations x minus 3, y equals 2, and 2x plus y equals negative 3 using row operations. Question 2. Consider the system x plus y equals 4 and 3x plus 3y equals a. For what value of a is the system consistent? For this value, find the solution set. Question 3. Solve the 3 by 3 system. X plus 4y plus 11z equals 7, x plus 6y plus 17z equals 9, and x plus 4y plus 8z equals 4. Question 4. Find the equation of the quadratic function y equals ax squared plus b x plus c that passes through the points negative 1, 3, 2, 9, and 4, negative 7. Question 5. Consider the system x plus 2y minus 2z equals 5, x minus y plus 3z equals negative 1, and x minus 7y plus kz equals negative k. For what value of k does the system have infinitely many solutions? Find the solution set in this case. Let's go through the solutions. Here is the solution for question 1. The system is x minus 3y equals 2 and 2x plus y equals negative 3. First, we write the augmented matrix, 1, negative 3, 2 in the first row, and 2, 1, negative 3 in the second. To get a 0 in the bottom left corner, we perform the operation R2 minus 2, R1, arrow, R2. The new matrix is 1, negative 3, 2 in the first row, and 0, 7, negative 7 in the second. Now we can simplify the second row by dividing by 7. We perform the operation 1/7 R2 arrow R2. The matrix is now 1, negative 3, 2 in the first row, and 0, 1, negative 1 in the second. Using back substitution, the second row gives us y equals negative 1. Substituting this into the first row's equation, x minus 3 times negative 1 equals 2, which gives x equals negative 1. The unique solution is x equals negative 1 and y equals negative 1. Here is the solution for question 2. The system is x plus y equals 4 and 3, x plus 3y equals a. The augmented matrix is 1, 1, 4 in the first row, and 3, 3, a in the second. To get a 0 in the bottom left corner, we perform the operation R2 minus 3, R1, arrow, R2. The new matrix is 1, 1, 4 in the first row, and 0, 0, a minus 12 in the second. For the system to be consistent, the second row must not lead to a contradiction. This means a minus 12 must be equal to 0. So a minus 12 equals 0, which means a must be 12. If a is not 12, the system is inconsistent and has no solutions. Now, let's find the solution set for a equals 12. The matrix becomes 1, 1, 4 in the first row and 0, 0, 0 in the second. The second row is redundant. We are left with one equation, x plus y equals 4. Since we have one equation and two unknowns, there are infinitely many solutions. We introduce a parameter. Let y equal t. Then x equals 4 minus t. The solution set is x equals 4 minus t, y equals t, where t is any real number. Here's the solution for question 3. The system is x plus 4y plus 11z equals 7, x plus 6y plus 17z equals 9, and x plus 4y plus 8z equals 4. The augmented matrix is 1, 4, 11, 7 in the first row, 1, 6, 17, 9 in the second, and 1, 4, 8, 4 in the third. First, we eliminate the x terms in the second and third rows. We perform R2 minus R1 arrow R2 and R3 minus R1 arrow R3. This gives us a new matrix. Now we can simplify the second and third rows. We perform 1/2 R2 arrow R2 and negative 1/3 R3 arrow R3. The matrix is now in row echelon form. Using back substitution, the third row gives us z equals 1. The second row gives us y plus 3 z equals 1. Substituting z equals 1 we find y equals -2. The first row gives us x plus 4y plus 11z equals 7. Substituting y and z, we find x equals 4. The unique solution is x equals 4, y equals -2, and z equals 1. Here is the solution for question 4. We need to find the quadratic function y equals ax squared plus bx plus c that passes through the points -1, 3, 2, 9, and 4, -7. Substituting the points into the equation gives us a system of three linear equations. For -1, 3, we get a minus b plus c equals 3. For 2, 9, we get 4a plus 2b plus c equals 9. For 4, -7, we get 16a plus 4b plus c equals -7. The augmented matrix is 1, -1, 1, 3 in the first row, 4, 2, 1, 9 in the second, and 16, 4, 1, -7 in the third. First, we eliminate the a terms in the second and third rows. We perform R2 minus 4 R1 arrow R2 and R3 minus 16 R1 arrow R3. This gives us a new matrix. Now let's simplify the second and third rows. We perform 1/6 R2 arrow R2 and 1/5 R3 arrow R3. This makes the numbers easier to work with. Next, we eliminate the b term in the third row. We perform R3 minus 4 R2 arrow R3. The new third row is 0, 0, -1, -9. The matrix is in row echelon form. Using backdash substitution, the third row gives us c equals 9. The second row gives us b minus 1/2, c equals -1/2. Substituting c equals 9, we find b equals 4. The first row gives us a minus b plus c equals 3. Substituting b and c, we find a equals -2. The unique solution is a equals -2, b equals 4, and c equals 9. Therefore, the equation of the quadratic function is y equals -2 x squared plus 4x plus 9. Here is the solution for question 5. We need to find the value of k, for which the system has infinitely many solutions, and then find the solution set. The augmented matrix is 1, 2, -2, 5 in the first row, 1, -1, 3, -1 in the second, and 1, -7, k, -k in the third. First, we eliminate the x terms in the second and third rows. We perform R2 minus R1 arrow R2 and R3 minus R1 arrow R3. This gives us a new matrix. Next, we eliminate the y term in the third row. We perform R3 minus 3, R2 arrow R3. The new third row is 0, 0, k, minus 13, 13 minus k. For the system to have infinitely many solutions, the third row must be all zeros. This means both k minus 13 and 13 minus k must be 0. This occurs when k equals 13. If k is not 13, the system has a unique solution. Now, let's find the solution set for k equals 13. The matrix becomes 1, 2, -2, 5 in the first row, 0, -3, 5, -6 in the second, and 0, 0, 0, 0 in the third. The third row is redundant. We have 2 equations and 3 unknowns, so we introduce a parameter. Let z equal t. From the second row, -3, y, plus 5z equals -6. Substituting z equals t, we find y equals 2 plus 5/3 t. From the first row, x plus 2y minus 2z equals 5. Substituting y and z, we find x equals 1 minus 4/3 t. That concludes our session on linear algebra and solving systems of linear equations. We've covered the essential theory and worked through several examples, including those with parameters which are common in IBHL exams. Remember, the key is to be systematic. Always start by writing the augmented matrix, then use row operations to reduce it to row echelon form. From there, you can easily determine the number of solutions and find them using back substitution. Keep practicing these techniques, and you'll build confidence in solving any system of linear equations you encounter. Thank you for watching.